All right, in question 3, it says, in problem number 8 on the divergence and curl worksheet, we prove that if F is conservative on an open and connected region D, then the curl of F is equal to 0. This is theorem 15.9 in section 15.5 in our text. All right, now I had mentioned that the converse of that statement was also true if the region D is also known to be simply connected. Okay, so we're going to, in this video, prove that converse statement using Stokes theorem. All right, so let's first recall what we did back on the divergence and curl worksheet before we get to the converse. Okay, so if F is conservative, then the claim is that the curl of the vector field is 0. Okay, well, if F is conservative, then by definition, it's equal to the gradient of some potential function phi. And we proved back on the divergence and curl worksheet that if you take the curl of the gradient of a function, then that's equal to 0. This just followed from Clairaut's theorem on the equality of the second order mixed partial derivatives. Okay, so you may want to go back to that video and review this. Okay, so again, if f is conservative, then taking its curl is really just taking the curl of a gradient field, and we proved that that was 0. Okay, so now we want to go the other direction. So in other words, if it's true that the curl is 0 on an open, connected, and simply connected region D, then our job is to prove that the vector field F is conservative. Okay, so to prove this, we are going to use the fact that an equivalent condition for the vector field F to be conservative is that the line integral of the field over any simple closed curve C in the region is equal to 0. Okay, so what we're going to do to start out is just let C be any simple closed curve in the region D. Our objective here is to show that the line integral of our vector field F over this curve C is equal to 0. All right, now it turns out, and this is an advanced result that we're just going to have to take on faith. It turns out that this additional assumption that our domain D is simply connected implies that a simple closed curve C in this region is the boundary of an orientable surface S in the region D. Okay, so with that, we can then apply Stokes theorem. Okay, because Stokes theorem will say that the integral around this boundary curve C is equal to the surface integral of the curl of our vector field over this surface S. And since we're assuming that the curl is equal to 0 everywhere on the region D, this surface integral then is just 0. And so in turn, the line integral over this simple closed curve C is equal to 0. And since C here is just any old simple closed curve, we in fact have proven that the line integral is equal to 0 for all simple closed curves C and D. And so now going back to section 15.3, right, we saw there that this is equivalent to F being conservative on the region. This was theorem 15.5. Okay, so cool. So this is a very nice result. And if as long as our domain D is known to be simply connected, in addition to being open and connected, then this provides us a really easy test to tell whether or not the vector field F is conservative. But of course, we have to be very careful. So in the next video, we'll actually see an example of a vector field where the curl is 0, but the vector field, in fact, is not conservative. And in the thing that's sort of going wrong, so to speak, there is that the domain D is not simply connected in that case. All right, so let's go and check that out next. I'll see you there.